Okay. Yeah. Should be fine. Okay, so I'll be talking something about enabling TPM 2.0 on coreboot-based devices. So, yeah, as it was previously mentioned, it will be on the APU platform. So, yeah. So this is more like a general overview. I won't dive deep into details. So yeah, let's begin. So we are the Trim Dev. We are maintenance of PC Engine's platforms. So I'm Kamil. Piotr has had a presentation yesterday, so he talked a little about Tiano core, what payload for coreboot. I will talk more about some hardware stuff. It should be quite simple. Alright, so the reasoning why we need that, because I believe security is important right now, especially in times of the IoT devices. So they have to be hardened against attacks because of recent, for example, in the news, maybe you heard something about the IoT botnets that emerge, and they are more and more danger to the whole internet network because they are used to some denial of service attacks. So yeah, so they should be hardened, and they are not always secure. So they are also, sometimes there should be a kind of proof we are running the good software, good firmware. So it's not filled with hard to remove rootkits or malware, persistent threats. So yeah. So what we want to show in this presentation is that some of our struggles when we were trying to enable secure boot in open firmware device. So yeah, this is not exactly thorough, but it could show just the overview of the process. So yeah, this is still work in progress, and there are many things to be done. So this is just the beginning, and also we are also beginners in this area. So we started to work in coreboot. I know coreboot since beginning of this year, so not so lot of experience. So I'm just learning, yeah. And TPM especially, because TPM is for me very recent stuff, like a month or something. Yeah, I don't know a lot about in this area, so sorry for any mistakes here. I hope that someone with greater experience would just correct me if I'm wrong, yeah. So right, so this is the agenda for the presentation. So first things will be some general security concepts overview. What's the definition of security, right? After that, there will be introduction to TPM 2.0, very short one, and just general introduction. So probably if someone needs to deep dive in this, there are plenty of materials out there to read, really. So after that, I will mention our TPM hardware that we are working on, and the current state of support in UEFI and SeaBIOS, and in coreboot, of course. Okay. Next, also state of support in Linux kernel and userspace tools, and verified boot in coreboot. After that, there will be some conclusions. Okay, so let's start. Yeah, so maybe you heard about it. For security, the CIA triad is often shown in different material as basic concepts of security. So the confidentiality, so the thing that we want to hide. So yeah, hiding the data, encrypting it, not showing third party our communications or things like that. After that, integrity. We have to be sure the data was not corrupted during the transmission. So yeah, and authorization, that we want to be sure that the data we received is from the sender that we trust and we know who it is, not some imposter. Yeah. And also sometimes in those materials are also showing the availability, so ensuring the data is available. So mitigations DDoS attacks, denial of service and things like that. Also non-reputation, so ensuring that the sender cannot deny sending our data. So, for example, that we know that there was a deal with someone and that the deal is still on, and not that the original sender denies that he sent this deal, so things like that. So those are general concepts of security. So what is TPM? TPM is basically crypto chip for boot verification, platform verification. It's used also for disk encryption and DRM stuff. So it's quite a general purpose, but most often it's used for ensuring that the platform we are running on is in correct state. So it's running good software. The software we want to run on it. It's slow by design. So this is a little bit about that way. The brute force attacks are not feasible because those will take too long to, for example, decrypt the keys, because it's not very fast in this area. So the TPM also contains cryptographic functions, contains hashing algorithms, key generation and protection mechanism. So random number generators, integrity measurements mechanism, so a lot of stuff. This is not a single purpose device, so yeah, it should be like that. Also, it uses various interfaces to connect platform. There are versions of it that support SPI, I2C, LPC. Yeah, and there is a concept of platform configuration registers that are in TPM. So those are shielded locations. Those are just registers used to store the state. And those are modifiable only by using a special extend function. And they are only resetable only by rebooting the system. There is no possibility of change the value of those registers after they are set, not using the extend function, which is quite special. We'll talk about later. Yeah, it's also got some secure storage, for example, for our keys that we generate on platforms, and we want to someplace to store them in a secure location. It's also passive, so it's not doing anything by itself. We have to do something about it. We have to initiate the communication of it. So it's only giving us mechanism to do something. It's not locking us out of anything. And it has also a possibility to restrict access to certain keys if measurements don't match. So this is mainly used for secure boot process and things like that. And yeah, so I will talk about it a little bit later. Okay, so there are two secure measure boot security during boot approach. So first one is secure boot that uses cryptographic functions, and secure boots prevents booting other firmware. So it's like testing the signatures of the firmware and testing that it's okay. And if it's not, then it prevents us from booting further because the software we check is not trusted. So secure boot needs some kind of root of trust. So the first step where we ensure that it's always trusted, something like hardware root of trust, or it could be a software one, but yeah, mainly it's a hybrid. So it asserts the boot. It's ensured that the boot is correct. And the second technique is measure, sometimes called trusted boot. So it uses hashes. So it doesn't check any signatures, it just hashes the firmware, for example. And it's used mainly for notification about the compromised firmware. And TPM is needed to do that, especially the extend PCR function, as I mentioned, to be secure. It proves the boot. It proves that we are booting the correct software, but it's not locking us out from booting it. Yeah. And it could be used to certify that the system is in expected state. Yeah. Okay, so what's this secure about, how it works? It's also starting from root of trust. So root of trust basically checks the signature of the next step, next phase before handing off of it. So it basically, as I said, it checks the signature. So the next step is responsible for checking the signature of another step and so on. So it basically creates something like chain of trust, starting from that root of trust. So this is really example, because sometimes the root of trust could be BIOS itself or some different thing. BIOS I meant as a general firmware for putting the platform system thing. So the measured boot differs that the next phase is hashed before handing off, and the hash value is stored in TPM. And the next phase also hashes the next step and extends the PCR. So the hashes work like that, the value in PCR is concatenated to the new hash, and then the new hash is computed and stored in the PCR. So it's like, it's just like measuring the boot state of each phase. Okay, so there are two main standards in use right now. It's TPM 1.2 and TPM 2.0. So TPM is just an international standard for secure microprocessor. Those are main specifications. There are many hardware implementations done by different companies like Infineon or Atmel, or I think, and much more. Yeah, and TPM 2.0 is not backwards compatible. It has completely different architecture. So yeah, main differences are supported algorithms, because TPM 1.2 is a little bit limited in this area. It has only SHA-1 and RSA and AAS support, and those algorithms are there, like hard-coded. There are no option to change that. But TPM 2.0 uses something like dynamic algorithm choices. So it supports SHA-1, SHA-256, RSA with different key sizes, elliptic curve cryptography, so ECC, and also AAS, and many more, because algorithms could be added by vendors as they see fit. So this is not hard-coded, let's say that. Yeah, and also TPM 1.2 stores the private keys that for the algorithms, and TPM 2.0 just stores the primary seeds. So seeds are like random numbers, and key derivation function is used to recreate the key from the random number. So the key derivation function is ensured that always the same key is created from the same seed. And thanks to it, it could support different algorithms which uses different keys, key sizes and things like that. Also, very big difference is the API. It has different commands. So, yeah. Okay, something about our hardware. So we are using the APU2 board. It's like that. And the TPM. TPM is SLB 9665 chip. So the Infineon one with the LPC interface, and it's connected right here to the LPC header. And that's what our platform looks like. So okay, so state of support in UEFI. UEFI was first to have TPM 2.0 support because this was to work with Microsoft, and Microsoft was first to leverage it. So it's first. Right now, coreboot supports TPM 2.0. So it's okay. There are drivers for the devices in this directory, and the TPM API is here, so it's in the library. I've seen that there is some redundancy, and also TPM API is not very much used in coreboot. It's used mainly in vboot, which I will talk later. And also SeaBIOS also supports TPM 2.0. It's also got some drivers in the API which is used. Okay, so state of support in Linux is support for TPM 2.0. It was added in 4.0 version of the kernel and improved in 4.4, and it's still improved, so there are many patches about that. TPM TIS kernel module is used for our case, especially. Resource Manager was added in 4.12. Resource Manager gives us parallel access, so we can access the TPM from different processes. Before it was single process access. So if any other process wanted to have access, it gets busy, error. Yeah. And there are 3 user space stacks available, as far as I know. The Intel one, the IBM one, and the Google's one, and they are all open source, so anyone can try something. There's also, I believe, TPM software emulators, so even if one doesn't have the TPM chip, he can play with it using the emulator. Yeah, so what it works initially. Initial boot was okay, it boots, so but there was a problem, because if we want to load the module from Linux, it has to use the force parameter, because according to Linux it was not correctly initialized, so yeah. But yeah, Intel's TPM 2.0 stack was able to communicate with the device, since Linux uses its own startup sequence to initialize the hardware. So the first problems, after checking the debug code, it was just obvious that the TPM chip was detected as the wrong one, as the SLB 966.0. It was version 1.2, so not TPM 2.0. This is a little bit strange, because the detection is done using the device and vendor ID, and it seems that SLB 9665 has the same one as the SLB 9660, but there should be an additional check to check that the chip is supporting TPM 2.0, and I believe it's not yet there. Yeah, and the problem was that even if this chip was detected as TPM 1.2, the startup sequence is really different, so the errors are occurring. So that's why it was not initialized. Yeah, TPM 2.0 spec is not easily readable. It's really, really difficult to read. So it's better to use right now the Linux code source, because it has really got good support for those chips and many functions describing the interface. So it's simpler to just use the source. Yeah, so I've used that approach, and I looked at the drivers of the Linux kernel to extract the correct initialization sequence. So this is the correct functions. It's used for manual startup too. And manual startup is described as the functions that work around the bad firmware. So if firmware is not initializing the TPM correctly, Linux can do that. And those are the functions that are used to do this. One part of this if is for this one is for the TPM 1.2, and this one is for the TPM 2.0, and correct startup sequence is here in these two defines. So, yeah, after I'm checking it, I could add the correct initialization sequence to coreboot source code. So yeah, as I mentioned, the same vendor ID and device ID in the SLB9660, and I've added some quick workarounds to force the coreboot to detect this chip as TPM 2.0, and I've added additional TPM 2.0 startup function that uses these new startup sequences, and now it's initialized correctly and Linux inserts TPM TIS module automatically. You don't have to use the force, so those manual startup functions are not used. So the support is here. Yeah, I posted some patches about it, but it was not production ready, and I see that in fact we are in the state of merging those drivers and this API library, because there is a little bit of code redundancy in there, because the TPM API in coreboot has those startup sequences, but they are not used in coreboot, just the vboot. So after this basic testing, so this is just output from the Intel's TPM 2.0 stack. So there are some capabilities of our chip. There is, for example, the version of the TPM that is supported, and here is identification of the chip. And as a hello world for every crypto chip devices, random number generator is used as for this. So here's 10 totally random bytes. Yeah, so as I talked about the coreboot and TPM 2.0, the driver, TPM 2.0 driver is already here, and as far as I understand it, it's used exclusively in vboot, at least for now, because I see that this is changing. There is some merge process going up. I believe Philip is behind this. So yeah. Yeah. So what's about the SeaBIOS? SeaBIOS also doesn't detect TPM 2.0 chip correctly, but it has support for the TPM 2.0. It looks like the procedures to detect the TPM version are not okay, especially the TPM hardware probe function. So I don't know, I have to look into it. Why is it? For my purposes in this presentation, I just hard-coded that we need to use the TPM 2.0 version, and it looks like it's fully working. So there is a TPM menu in the SeaBIOS, and also I can see that measurements are being done, so the TPM PCRs are extended in those functions. So really in loading option ROMs, and also these second functions, it's like measuring the master boot record of the boot device. These could measure the CD-ROM that's used. Yeah, and about the verified boot in coreboot. Verified boot is a hybrid technique of secure boot and measure boot. It uses the TPM, and also it checks the signature of the steps in loading the firmware. So this is like short description of what I will talk about. So general concept about this, how the firmware image looks like, because it's not simple. And the vboot is mainly used in Chromebooks. So this is Google territory. Yeah, and also I will talk how it integrates with coreboot and SeaBIOS, and DevCharge is used in Chromebooks as a SeaBIOS alternative. So yeah, so verified boot has a specific boot flow. It starts in read-only part of the flash where boot block exists. So this is like the end of the flash. It could, yeah, and first stage is the stage where vboot is. And the first stage could be separate, or it could be the part of the boot block here. Okay. Okay, so First thing is that the control from boot block is passed directly to the var stage. Var stage exists also in the read-only part. And var stage loads the keys to check the read-write section of firmware, which I will talk about in a minute. And if this fails, it falls back to read-only firmware and it boots in recovery mode. Okay, so what we want to do if we want to enable the verified boot. It's not very trivial to implement really, because mainly of special layout that we need. So there are several CBFS regions. As I mentioned, there is a read-only region which also contains coreboot, and SeaBIOS is like a recovery stage. And also there are two read-write regions which are named FW main A, FW main B, and there is a also region which is called legacy for purposes of for putting some another firmware. It's not used in normal boot flow. Only these first three are used. So our platform uses hardware blobs, of course, like almost everything. So the two blobs that are there is ECC', which is a kind of blob that is initializing the memory, the RAM correctly, and the AMD FW. So this is like firmware for the PSP, which is AMD equivalent of manageability engine. Okay, so what steps are need to be taken to enable that? First, we need to create the FMD file. FMD file is a firmware layout file. So we need to place the blocks in correct places. They have to have specific offsets in the firmware to load correctly. So the read-only section should be also placed correctly. Boot block has to be at the end of the flash, because that's the place when it starts. So it takes a bit of hacking to move all those little things and be okay with this. So also there is a need to add some boilerplate function to mainboard directory to enable vboot, because vboot expects some of those functions, like for example get write protect states, which returns the state of the write protect jumper, for example, in our case. Third thing is we have to enable vboot in config, and also config collect timestamps, which is also needed for vboot. And we also have to point to config fmd file to our flash file. And some hacking with blobs adding to firmware was required, because for the APU they are just added to the CBFS, but this is several CBFSs and they are need to be placed in the firmware, not in the CBFS. Okay, so this is like FMD file looks like. So those are different sections with offsets, and here are the offsets in the upper section, and this is the length of this region. So the first region is Apple firmware region, and it has to be placed on this offset in flash. Next to are the read-write sections of the firmware. There are two sub-FSs, read-write sub-FSs with firmware. Also there is a vblock, which is important for vboot. Vblock contains signatures for the firmware that is being loaded. There is this legacy component and read-only section. Read-only section is protected from writes by write protect, hardware write protect locking of the SPI flash. So here is the adjacent firmware which have to be on this offset. And the coreboot CBFS is at the end, because boot block is there and it has to be at the end of the flash. So yeah, it took a little bit of hacking to place it exactly here because those offsets are not absolute. They are just offsets in these specific sections. So yeah, after this hacking, we started the machine, and it from the logs, it looks like everything is really working out. So the vblog in the first from the first section, so this is the vblog A, was found correctly, and key block signatures were being checked, and we would hand it off the boot sequence to the proper stage. So this stage is here. This stage contains coreboot and SeaBIOS and the rest of them. So yeah, this was our first test. So what's our further work to that? So we need to enable verified boot capabilities in coreboot and especially in SeaBIOS. In SeaBIOS, because I believe SeaBIOS has only measurement being done, but those signatures are not checked. So SeaBIOS should check the signature of the bootloader. We have secure boot-capable bootloader, which is a trusted graph. We need to investigate the usage of vboot, how it works exactly, because we only scratch the surface, so we don't know exactly if it's the correct boot flow. It really needs to be tested out. We need to prove it really works, because right now we have some idea how it works and it looks like it's working, but we are not sure, and if we want to be really secure, we need to prove it. And yeah, it needs a lot of testing to be sure. And there is also an open question, is it possible to harden it even more? So what about the PSP? PSP is doing something and we don't know what it's doing, and it could be malicious. So yeah, the conclusion is that adding the new chip in coreboot right now is quite easy because the main support is there. So it only took changing of device ID and vendor ID and correcting the identification. So this is not a big deal. Using the source brings better results than using this huge spec. Yeah, that's a nice idea, because here the specs are, I don't know, written from machines. So yeah, understanding the platform boot process, block placement is really crucial here to enable coreboot. This took the most time to create the FMD file. So yeah, and I believe there could be verified boot capability of custom coreboot platforms, not only Chromebooks, and that should be nice use case for open firmware like here. So also there was some recent news about this new attack that were proven that Infineon's hardware is a little bit vulnerable. So the RSA private key could be decoded from public key, but the exact specifics are not yet known. I believe they will be published soon, I believe. So there are tools to test your keys. Also, elliptic cryptographic keys are not affected in this attack, and if RSA primes that are used to generate those keys are really random numbers, this attack is not viable. This was a problem in RSA library used in this Infineon's hardware. So we believe that our chip is also affected. And these were some sources that I used. Also, I've used some previous presentations from previous coreboot conference. It was done by Philip. So it showed me a little bit about how it all works. So it's a very good source. And thanks. That's all for this.
So we now get the questions. Are there any?
So I don't know much about the TPM. Could you go to slide 9 because there was a thing I didn't understand on slide 9.
Slide 9?
Yeah, sorry about that.
Yeah.
So it says root of trust hashes files, then it said TPM's PCR is extended. That means it was already extended before.
No, it has, after the booting, the PCRs are zeroed.
Yeah.
I don't know if it's some starting hash that is used to hash 0 and it's some of it. I don't exactly know, so I can tell about it. But it's some starting point and always the same.
Yeah. So in other words, for this to work, it's the TPM's PCR was extended. I just know what I do. So it's like you extend it and then you're able to use it. I just have to read.
Okay.
Yeah.
Okay. Yeah. Maybe
there's another question.
This is a little application. The main board you use it so the original main board was solved without TPM.
Yeah.
It's okay.
Yeah.
You out separately the module.
Yeah. Yeah. That's
You just grab it and import it. You have to do some hacks, other hacks.
Yeah, these exact modules was provided by the PC engine, so they are sure to work with their platform, so it needs no hacking. But I've seen some materials on the internet that someone just plugs there some general purpose TPM from mainboard, but he needed to use different pinout, so it needed some hacking.
So even for the TPM, is the same manufacturer which sold you got the little view from which engines?
Yeah, so this is the same vendor.
So the pinout is opt, it's no for the review.
Yeah, that's true. Yeah, those pinouts are not exactly standard, so it could differ between vendors. So different TPM modules for different mainboards could not be compatible. But the chip itself should be, if it uses the LPC interface, it will almost always need to change the pinout.
The LPC is standardized.
Yeah, that's true, but I've seen that it's not always the case that it sometimes needs some hacking, yes. So I don't know why, because I know the LPC is standardized.
Any more questions?
Hi, so the vulnerability you have discovered, the opinion chips, are there even latest chips affected of that?
I believe it could be solved by the firmware update, firmware of the TPM update.
Oh, really? Is that the firmware side which you can update?
Yeah, because TPMs are really just the microcontrollers, so they contain some firmware. It's another blob. Yeah. Yeah, that's it.
Any more questions?
And speaking about the firmware inside the TPM, you didn't have to do any preparation, any initialization of the TPM. You just plug it.
Yeah.
It's already initialized with the good firmware.
Yeah, that's correct. That's correct. The only needed step is some sequences that we need to send to initialize it, but this is just a command. This is not a loading of the new firmware.
Do you think that this is the case for all the TPM which can be mounted?
Yeah, I believe so. They should be the same because
no
this.
need to load a special firmware.
Yeah.
Okay, we have time for a few more questions.
Just a comment about the Roca. It is known, if I recall correctly, from January by Infineo, and YubiKey use Infineo, and YubiKey claimed that since June all devices are correct and they offer free replacement for vulnerable devices.
Any additional questions? No? Oh, okay.
Sorry, just one more.
No, it's okay. We have time.
So do you think the time kept in TPM could be used as a general source of time? I don't know how far the time goes. I saw it looked like a year and date.
Sorry,
If you have a system with no CMOS or something, would the TPM provide a useful replacement for a time, time of the year clock or?
system time.
Yeah.
Good question. I have no idea.
Okay, so let's wrap it up. Give another round of applause for Kamil.